So welcome everybody. This is the Flow seminar, where Flow stands for Federated Learning One Word Seminar, and this seminar was created to provide a global online forum for the dissemination of latest scientific research in all aspects of federated learning. This includes, but not limited to, distributed optimization, learning algorithms, privacy, cryptography, personalization, different aspects of systems, hardware, and many more. So today is my great pleasure to introduce you our speaker, Martin Takáč, who is an associate professor at the Mohammed bin Zayed University of Artificial Intelligence in UAE. And before joining MBZUAI, he was an associate professor in the Department of Industrial and Systems Engineering in Lehigh University, where he's been since 2014. And he receives his bachelor and master both in mathematics from Comenius University in Slovakia and PhD degree from the University of Edinburgh. And in his research, he focuses on the design and analysis of algorithms for machine learning, applications of machine learning optimization, and HPC. And today he's going to tell us more about his work on federated learning, titled Federated Learning Second Order Framework via Compression and Sketching. So thank you, Martin, for agreeing to give a talk. Please, floor is yours.
Also, thanks to the organizer for inviting me to give this talk. Also, this is joint work with my students, my postdoc, and some collaborators from all around the world. Basically, I think Alexander is in Russia, Rach in New Zealand, and others are basically working with me here. Before going to speak about my talk, I want to just say this is based on some paper which is already online, which has been mentioned below. But also we mentioned something which is ongoing work and basically some kind of ideas and so on as we go, okay? Before going to present my work, I also want to mention that we have some open positions, postdocs, PhDs, masters, and also some visitors. So basically if you know someone or you yourself, you want to apply, please shoot me email on this university email which I mentioned here. Okay, so I'm pretty sure everyone knows what is federated learning, so I can maybe cover the first few slides quite quickly. So basically in this setting, we assume we have multiple devices, and basically each device has some private data, which we don't really want to share, okay? Also, many times the communication between the devices can be quite limited. So basically, therefore, we want to maybe communicate as little as possible, because also when you communicate, maybe someone can discover something with your private data, or other ways saying also the communication can be expensive because maybe you need to send data over the network or data in your phones and so on. It's very expensive. Also, somehow very crucial thing what I want to mention is that many times the data, let's say the RAM and the memory on each device can be quite small. So basically, therefore, some operations cannot be really performed efficiently on phones or basically on some small devices. And actually, there are so many challenges. I don't want to mention all of them. I just want to keep the most important for this talk. And also basically, as I say, in this case, I have different functions. Again, I will define some models on every single device. This is F1, F2 up to Fk. I will have K machines in total. And each function depends on the local data, which is Xi, Yi, 1 or 2 or up to K, okay? So basically we have a local data on every single machine. I want to basically find this problem. I want to find the best way, which will minimize the expected value, or basically the average of those functions on different devices. And we can also assume that all those machines can communicate with some centralized server or basically cloud in my slides, okay? And also basically there are so many challenges. Let's say one of them can be that some machines can participate all the time. So basically this partial participation challenge, but in this talk, I will not really think about this one for simplicity, and we assume all the devices can always communicate when requested, okay? And also for simplicity, I will call this average of the functions just function FW, okay? So basically my goal is to find the best W, which minimize this FW function. Okay, and one of the baselines or one of the simplest algorithms you can think about is this FedHGD. So basically how it works, you have those K devices, each of them will receive some current iterate WT, and afterwards they will compute, let's say, the gradient using their own local data, Maybe it can be the full gradient or just stochastic gradient estimate, doesn't matter. And afterwards, you communicate them to the cloud or to the server, which will compute the average of those vectors. And then you just use this average just to update your local, basically this parameter WT to obtain WT plus 1. In this case, my eta t will be some kind of learning rate, and you somehow understand basically different schedules, how to choose eta t. Let's say if you have a convex problem, you compute the function deterministically, you can just choose constant step size. Otherwise, maybe step size has to be decreased over time. But actually, if you think about this setting, maybe if the communication is so expensive, maybe you can use some kind of compression or quantization for those vectors, right? This can definitely decrease the amount of communication basically by a factor of 10. Let's say instead of sending 64 bits, let's say doubles, you can go to only, let's say, 6 bits or 10 bits, and you will save some communication. But this will not decrease the communication dramatically. So the question would be, how can I really decrease number of iterations or communication rounds a lot, okay? I just also mentioned this compression. Basically, for example, the easiest one, if I have some vector x, I can define this unbiased random compression such that expectation of this compressed vector will be the vector itself. And also the second moment of this compression will be some bounded by the magnitude of the x. So basically you can see if I want to have compression, which is not creating too much noise, ideally, the x or the thing that I compress should go to 0, okay? In this case, it's somehow good because it will be unbiased, and also my variance will be actually going down if the x or the quantity I want to compress or quantize will be also going to 0, okay? For example, in this case, I get 0.75. I can just use random compression to send value 0 or 1. So in this case, I can just use 1-bit random compression to compress this number to either 0 or 1 bit. And those are the probabilities how you can do it. So let's now speak about one interesting work. I think this was like 2015 by Lin Xiao and co-authors, which is called DISCO. It's about distributed optimization of self-concordant empirical loss. I think this is nothing to do with FL. Maybe the FL was not really the thing at the time, but I think it's still interesting to think about this algorithm. So let's motivate this one. Let's think about the Newton method and CG. So imagine I have these K devices. Each of them can compute the gradient, and maybe they can also compute Hessian. So the Newton direction, basically, we think about, I want to use Newton method to minimize this function. You still need to compute the average of the Hessians, and then average of the gradients. And afterwards, I want to solve this system of linear equations to find the P. Basically, the P will be nothing else, just the average of the Hessian or Hessians of the different devices, inverse times the gradient. Again, you actually don't really want to compute this one as inversion because this can be very expensive, but maybe you can use some iterative scheme to solve this one, okay? So basically in the DISCO, what they said, hey, I know some perfect iterative scheme, it's called CG, conjugate gradient. So basically in the conjugate gradient, it's a really algorithm to solve these system linear equations where A will be symmetric and positive definite. And basically it works in such a way that you iterate basically this main loop and you are getting a solution in this Kirchhoff subspace. So basically if I run this CG, let's say for 3 steps, I will find a solution in the Kirchhoff subspace spanned by B, A, B, and A squared times B. Again, in our case, A will be the Hessian and the B will be the gradient, okay? So basically, if I just use only one iteration of this CG, my X, which will be the direction of this sub-problem, will be just the gradient direction scaled by some local curvature. Again, you can see here in the algorithm, what is somehow good is that it's trying to solve this system of linear equations. And every step, you just need one Hessian vector product. Again, A is my Hessian. Now see here, when I start with 0, then my residuum is just the gradient, the B. And afterwards, in the algorithm, all I do is multiply A times P. So all I need to do is just multiply Hessian by a vector. And basically, as linear and coordinate this and find out, actually, it's super easy to do, okay? And basically, the convergence of the CG depends on the spectrum of the matrix A. If all those eigenvalues are actually equal to each other, then just one CG step is sufficient to solve it. If basically my eigenvalues are somehow clustered, maybe on 3 different clusters, I just need to make only 3 CG steps to solve this one with high accuracy. But actually, it's very hard to just hope that this Hessian will have very good eigenvalues or some cluster eigenvalues. So this is the bad news. Because maybe in the worst case, I will need to make here almost like these steps where this is the dimension of my space, number of parameters, right? In the worst case, I need to make these steps. If the eigenvalues are clustered, then I will need maybe only 3 steps to really solve this one into high accuracy, okay? Which is basically a good thing and also a bad thing, because there is no hope that I can hope that my Hessian will be nicely conditioned. But basically, also there's a question I always talk to students and some collaborators, and they always say that Hessian vector multiplication is very expensive because I need to first store the Hessian and then compute the Hessian vector product. It turns out it's not really true because computation of Hessian vector product is super, super cheap. Actually, the cost is the same as computation of gradient. Why? Because Hessian vector product is nothing else, just computing gradient of this number. Again, this is my gradient, and I compute dot product between gradient and the vector itself. So this is just scalar. I can compute gradient one more time, which basically will turn out to be the same stuff. I can use, again, PyTorch, automated differentiation. I can really compute Hessian vector product only with the cost of 2 gradient computation, okay? So this is not really the issue. So basically, how can we use this, the whole stuff here, the CG? I need to compute the right-hand side, which is the gradient. I need to communicate gradients. Afterwards, in each step here, I will get some vector P. I need to compute Hessian vector product. So basically, in every step, I will get the model parameters, compute my local gradient, send to the server, to the cloud. It will compute basically maybe the average of the gradients or some different directions, some vector space. And afterwards, I compute my local Hessian vector product. I send to the server, and he can compute the average of those vectors from different workers, which is pretty easy. But still, it doesn't guarantee that the Hessian will be very nice. So what is the different strategy which was basically proposed in the DISCO paper was this one. Imagine I have some good precondition matrix M, okay? If I have some matrix M, which is very similar to the Hessian, what can I do? I can just maybe decompose this M inverse as E times E, because again, this M will be some symmetric. So what I can do, I can multiply both equations by E from the left. Then maybe I can use transformation that my X will be equals E times Y. And basically afterwards, I can use CG to solve this problem. Again, my matrix here will be still positive definite and so symmetric. Also, the right-hand side is just some vector, that's fine. But we are hoping that if this M was good enough, was somehow equal to the Hessian, then my EAE will be the same as identity. And therefore, I want to use CG for this problem here. I just need only one single step. Again, I will not really have this M equal to the Hessian, but maybe it can be very close to the Hessian. And therefore, I will need only few CG steps. So basically saying, if you know some good preconditioning, ideally the Hessian, the full Hessian, then I will need only one CG steps. And usually, basically, what you can do, you can just maybe run Newton problem for maybe only like 10 steps. That's it, right? If you have good enough M, then maybe the whole communication will be just 10 CG steps, right? Or 10 iterations of Newton method. Each will just need only one CG step. But this assumes that M will be very close to the true Hessian, which is not really a reasonable assumption, okay? So basically, what was the idea in the DISCO paper? They assumed that I have some kind of homogeneous data. So every Hessian on every single worker was somehow comparable to each other. And therefore, also my hashing locally on the first machine was the same as average of the hashings, right? If this is the case, basically what I can define this M, my local preconditioning, as the hashing only on the first machine and plus some kind of small regularization. And afterwards, what I will basically do in the CAG step, I will just compute locally only on the first machine these updates. Again, I will do preconditioning only on one machine, maybe using my local data, which is pretty nice because you don't need to communicate anything. You just basically really transfer the burden of running many CG steps into one machine, maybe the fastest machine, I don't care. And he will try to compute this M inverse times I, or saying differently, M times S is equals to I, okay? And because this will be done only on one machine, I don't need to do any communication. I don't need to share any data, nothing like this. I will just compute this preconditioning only for every iteration of CG, only on one machine. Okay, and this will show that actually the number of communications needed, really iterations, and always in every iteration, someone solving the CG will need only so many steps, right? Only so many communications I need to do. F of W minus F star, maybe this will be, if you scale your data perfectly, you use logistic loss, then this will be just 0.65, so 1, that's nothing. Then the log 1 of epsilon, which again, if you don't want to have high accuracy, it's nothing. And then square root of 1 plus mu over L. Actually, L1 will be L2 regularization for the logistic regression, for example. And the mu will be, what do you think? What is mu? The mu should be how far is my preconditioning of my local hashing from the true hashing of the whole function, right? So basically, the mu is some kind of bound between the hashing and the hashing on the first device, which is doing the preconditioning step, right? Again, if my hashings are the same, then mu will be 0, and therefore I don't need to do actually almost anything, right? Which also makes sense. Because in this case, I really just use Newton method. I just need to use only one CG step, right? So therefore it's almost like perfect. But again, like this is not really true for many different data sets when we don't have this condition. In the worst case, maybe mu will be like super large, right? And therefore you will need a lot of communication. So we didn't really gain anything, right? It's still basically almost like accelerated gradient descent or basically proc skip, where this one becomes almost like some kind of L over mu. So this can be very, very large, okay? So basically, what was the way to solve this problem? Actually, there's like this line of research, a very good papers from Peter Richter group about FedNL, okay? I just mentioned only a few of them because I didn't want to have the whole slide mentioned by so many papers. But basically, the idea inside was, I still want to use this Newton direction, and I still want to basically compute the average of the hashings on the devices inverse times the gradient, right? But we want to discuss this is like so expensive to do because sending hashings is impossible. For example, when your model size is just 50,000, the size of hashing can be almost like, I don't know, 8 gigabytes. So this is like super, super large, right? So basically what I proposed was some small trick. I will assume every device will have some kind of estimate of the hashing. Also, I will assume that the server will know the average of those matrices, okay? And basically every iteration, when you run this FedNL, you compute gradients, you send them to the server, to the cloud, which can compute the average. Also, I would like to send the hashings, but I know I cannot send the hashings because it's expensive. So basically what I will send the gradient. I will compute actually difference between my local estimate of the hashing and my local hashing. I will maybe send this one, but still expensive. So I will use compression, maybe top K or different compression which you want, doesn't matter now. And I will send this compressed version of the difference of the local estimate of the hashing and my local hashing to the server, okay? And afterwards, I will update my local estimate of the hashing by alpha times the SJ, okay? Again, on the J machine, this is how I estimate basically the message I should send to the server. It tells him that how far is my hashon from the estimate of the hashon, basically, which you know about. And afterwards, I also need to update this age. And what will the server do or the cloud do? He will receive all those messages, basically about the estimates for the hashons. He will also compute the median, or basically the average of the gradients. Okay, so this is my gradient of the function. And afterwards, I can compute this almost like a Newton step, right? Almost like a Newton step. I take my local estimate, which is nothing else, just average of the estimates of the hashons from devices. I will need to put some small dumping here. So basically LT will really depend on some quantities, how good the hashons are on devices. I do inverse times the gradient, okay? So this is what I do on the server. Afterwards, I can send this new iterate to the workers and they can start working on the next gradient and the hashon computation and so on. And afterwards, I will update this age by adding again alpha plus this ST. So what is nice about this, the server doesn't really care about the individual values of the local estimates of the hashon. He doesn't care about this one because he just update the average of them. Remember, I update my age local by adding alpha S. And what the server is doing, basically, he computed average of those S's, and now we'll define this HT to be like this. So basically, you can somehow show that this HT plus 1 will be just average of the local estimates of the hashons on all those devices, okay? And also, basically, what is somehow like nice about this method is that as you're converging, maybe those HTs will be getting closer to hashon, and therefore this one will turn to the Newton step, right? It will be hashon inverse times gradient, which is nice. And also you have this quadratic local convergence, basically when you start, or basically once you get close enough to the optimal solution, there's some radius where your algorithm basically become very, very fast, which is nice, okay? And if you go back to this one, you can start thinking, can I store the hashon? Or basically, can I even do this step on device? Remember, as I mentioned, when your size is like 50,000, which has number of parameters, which is still nothing, the size of hashon will be 4.6 gigabytes, the same for storing this vector H, right? So basically sending this one or running this one on device can be very expensive. Also computing the hashon itself can be also quite expensive. Not only the storage, but also the computation cost. So basically in this work, we try to see what can I do differently. But before I start speaking about this one, are there any questions you want to ask? Any questions so far? Okay, if there are no questions, I can
please,
just...
as a reminder, if you have any questions, just post it to the chat or just raise your hand. Yeah, at the moment, there are no questions in the chat or raise your hand.
Just give you like
so I guess
1 minute to think if you have any question.
Mm-hmm.
But again, I like this work a lot, this Federated, because I think this idea introducing this like local estimates of the hashons on devices, I think this is pretty nice. And then you just start using the fact that I just need to communicate the difference between the age and the hashon. I can compress, I can quantize, and so on. I can send to the server. He just update the estimate of the hashon, which is the average of the function's hashon. Okay, so let's now think about what can I do to not really require the workers or devices, for example, your phones, again, to really store additional maybe 9 gigabytes of data for this small model. But again, like it's not about this one, it's also about computation of the hashon. It's quite expensive to compute, okay? So basically what we try to do in this work, we try to shift the need to store the hashon estimates on devices to the cloud, okay? We really want to make this burden not for devices, but only for the cloud. Because still, even let's say if the age will be, let's say, 10 gigabytes, I don't care. You have, let's say, 1,000 devices, you can still store 1 terabyte on cloud. You cannot store 10 gigabyte on workers, right? And also, basically, the second thing which I mentioned is that computing the hashon is very expensive. But we already understand from the CG what I was speaking before computing Hessian vector product is quite cheap. Computing Hessian vector product, once you have gradient already computed, is just the same cost. So basically, computing Hessian vector product is fine. So maybe I will only need to compute Hessian vector products on devices, not the Hessian, just Hessian vector product. Should be allowed to do not only Hessian vector product, but maybe do Hessian matrix product, where M will be, where the S will be D by M, where M will be usually small, like 1, 2, or 4, or 8. Okay, but this is still fast because you can compute Hessian vector products quite efficiently on devices. Okay. And basically, we will only communicate maybe these Hessian vector products to the cloud. It turns out this is also not good because I mentioned at the beginning, if you want to somehow quantize something, ideally, this one should go to 0, right? Again, there is no hope that my Hessian vector products will go to 0. So I can just quantize this one. It's not really good, right? So basically, what you decided to do in this paper is to not communicate these Hessian vector products, but somehow use compression in some efficient way. I really want to send something which should go to 0, okay? So basically, how we do it, remember, my server or my cloud already know my estimates of the Hessians, right? So what I can do, I can just choose the same ST both on device, also on the server, right? And this can be actually very easily just pick some random seed which depends on number of iterations and so on. And then I can just choose this ST on a cloud. I can also generate this ST on devices. Afterwards, the server will have to send me this Hessian times S, okay, over the network. I need to send this one to the client. Afterwards, the client will compute the full gradient on his function, will compute the Hessian vector products or Hessian matrix product. And ideally, if my H is getting closer to the true Hessian of my device, then this vector here or this matrix here will be the same as the one I receive from the worker, from the server, sorry. So basically what I will do, I will compute the difference between my local Hessian times vector or matrix minus the H times the sketch matrix S, which was generated on the server, right? And I will use compression on this quantity. Again, ideally, as I'm converging to optimal solution, and also my H is converging to the Hessian, the local Hessian, this quantity will go to 0, okay, which is pretty nice. And afterwards, I will send this message to the server, to the cloud, and he can perform the update. So basically, server will update my estimates of the Hessian to the new one, and also he can compute the average of the gradients, and then maybe use this H as a Hessian approximation and compute the Newton step, okay? And then I will get the next iteration, WT plus 1. So again, what's happening here? I will send 2 messages from the cloud to the worker. One is the WT, which is the current iterate. Also, I will sketch using the same random seed. I compute like matrix ST. I will sketch my local estimate of the Hessian, which is stored on the cluster on a cloud. I will also send this matrix, okay? Afterwards, worker will compute the gradient of this function. Will compute Hessian times S. Again, this is cheap on a device. Then I compare the difference between this and this message I received from the server. I will compute compression of this one and send this one to the cloud, okay? And then I will do the next step on the cloud. Yes?
Yeah, there are a couple of questions from Konstantin in the chat, so I'll just unmute him and he can ask himself. Yeah, please go ahead, Konstantin.
So can you highlight what's M? So how M is smaller than D?
Okay, so M is almost just a memory. Let's say when you have quasi-Newton methods, M is usually chosen, let's say like 5 or 10. So in my case, M will be the size of the sketch matrix, okay? Usually you will see the results. Usually M is 1 or 2 are good enough, okay?
So
of course,
as a user of a Flex, I can select M as a constant, just 5.
Yes, M should be constant, let's say 1 or 2 or 4.
Okay.
Again, if you choose M larger, this really means your communication will be more expensive, right? Because you are sketching the Hessian using more vectors, right? So the size of the message here will be D times M, okay? Again, if you multiply Hessian, which is D by D by M, I will get D by M matrix. So again, if you choose M very large, I need to communicate much more, okay? On the other hand, choosing larger M means I will get better estimate of the Hessian much quicker, but there's a cost because you need to communicate much more, right?
Can you say,
yes, go ahead.
Can you say also about ST? So what is it? Is it a symmetric matrix? So
no,
what
ST
information needed
ST is just random matrix which you can add. Maybe from unit sphere, doesn't matter. Again, ST is just random sketch. Maybe each column will be, you can just normalize them such that every column will be basically norm 1, doesn't matter actually. It can be just Gaussian matrix to just choose randomly ST. It is just random sketch of the Hessian.
Okay, so as a user of Flex for ST matrix, ST is not depend on a gradient or current iterate.
No, doesn't.
Okay.
But I will speak about some extension that maybe this is not the best thing, and I will speak about this one in maybe like few slides, okay? But ST is just random matrix, okay?
One thing that I wanted to highlight, so in Federated, for example, this compressor operator, it's applied for Hessian, which is in the, like if the function is continuously twice differentiable, then the matrix is symmetric. So during apply compressor operator, I apply, for example, this for top triangle part of the Hessian, but in some sense, I'm for free obtain information about lower triangle part. And if select ST is not symmetric, then it breaks symmetry, and I just sent less information by factor of 2. Okay.
Yeah, so actually, I know what they're speaking about. So basically, the claim was that when you go to FedNL here, I know that this matrix will be symmetric, right? So if my H was symmetric at the beginning, which maybe it was, because maybe choose H to be the Hessian at the beginning, then this matrix will be still symmetric. So when you do compression, you just maybe just look at the upper triangle, triangular matrix, and let's say choose the k largest elements in absolute value, and you only send those, but you also basically updating the lower triangle as well. That's correct. We don't have it in our case. We don't. So basically in Flex, my S will be a square. It's basically in square. It's rectangular matrix, and basically what you are sending is this H times S. Again, it's a matrix which is D by M. Always I'll say choose M1, okay? So just do one random direction, and you're sketching the Hessian in this direction, okay? That's it. So basically just one vector. And afterwards here, what I communicate is again difference of two vectors, right? Again, if M is 1, I just have one vector, which is the sketch of the Hessian in this direction. The same about sketching the estimate of the Hessian in this direction. And basically afterwards I compute difference and I compress this one, and that's the message I will send to the server. Okay.
Yeah, thank you.
To now see why this is important and why you don't lose symmetry is the way I update the H on the server, right? So basically after I receive these gradients, I need this one to compute the average of the gradients, basically the right-hand side for the Newton system. Also, I need to update this H, right? Again, I had some belief, then I choose some random direction ST. Now I learned that my belief is very off, right? Because maybe if the message here is not 0, this means in this random direction ST, the true Hessian is very different from my belief, right? Which means I have to update my H. Because again, what I obtain is that it's very different, right? Does that make sense or not?
Yeah, thank you. Yeah.
Okay, cool. So basically now question would be, how can I update this H from HT to HT plus 1 for every single device? And afterwards, what I can do, I can just use the, again, average of those H to compute basically the Newton step afterwards, because I will have on a cloud the average of the gradients. Now I will also have the new H, which is estimate of the Hessian for every single device. can compute average of those guys and do the inverse and multiply by the full gradient, okay? And then I will obtain my new WT plus 1.
Yeah,
Actually, there's one more.
another...
Go ahead.
Yeah, go ahead. And there is one more question in the chat by Nurul. So he raised hand. Let me just unmute him. Yeah, please go ahead, Nurul.
Yeah, please. Thank you. So I just want to know the difference between HT and the Hessian of Fj. It looks me both are Hessian.
Again, Hessian of the function f
Mm-hmm.
is just average of those Hessians here. I think you can see my mouse, right?
Yeah, I can.
Again, the same like H is just estimate of the Hessian. Maybe it's not perfect, right? If you have HJTs, the estimate of the Hessian would be average of those HTGs over J, right? Basically, J is the machine number. You have 1 up to K. So basically, the estimate of the Hessian I would use will be the average of those matrices for different J's from 1 up to K. Okay.
Okay.
So again, the same basically as you have the, I don't know if I can annotate. Maybe I can. You can.
Where do you store this? I mean the Hessian of Fj.
So I need to store these HJTs on a server on the cloud.
Oh,
Again, I
okay.
need to store this again. Before, basically, for FedNL, this AJT was stored on the devices, right? And also, basically, for the FedNL, what we did, we computed basically this one. You computed on device the Hessian. You also had on device this AHJT, and you had it on the device. You compute the difference, and then you use some compression. Basically, as was said before, maybe top K, only from the upper triangular matrix. I don't care, right?
Yeah.
But this was done before. Again, there are two drawbacks. You need to store this one on devices. And many times if you think about your phones, I don't know how much you have memory, but I have maybe like 1 GB free memory, right? It tells me I cannot do this algorithm for large enough models, right? Because again, there's high requirement for the device to store the Hessian and also the Hessian estimate, which is now shared with the server. So therefore, basically, someone said, let's try to shift this burden from device to the cloud. Also, what there's some claim is that computing Hessian itself is super expensive. But computing Hessian vector product for only few vectors, it's very fast, okay? Let's say when I choose M to be 1, I just have only one sketch. I can compute Hessian vector product, this Hessian times S, with the same cost as computing gradient, which is nothing, okay? So if computation gradient is, let's say 1 second, I can also compute H Hessian times S, where it's basically just 1 column, and again in 1 second. It's nothing, okay? Where here computing the full Hessian could be really just D times computational gradient. It's very expensive to compute, okay? So basically, therefore, someone said in Flex, we don't want to compute the Hessian at all. I just want to only sketch the Hessian by some sketch matrix S. Okay, that's all what I need to do. To compute Hessian times S, we know this is very efficient. It's just the same cost as gradient times M. Okay. So therefore, basically, some say don't choose M very large, just choose M like 1 or 2 if you want to. Okay. Afterwards, basically, first of all, it's much more expensive to compute Hessian vector products or Hessian matrix product, and also need to communicate much more bits because I need to communicate this matrix, which will be D times M. Okay, it's quite expensive afterwards. Okay, so basically, understand. Yeah, any question?
So yeah, so this computation, I mean, in the last equation, CTJ, it happens in the server, right?
No, this is still happening on worker. Again, worker computes the gradient, compute the Hessian times S, which is basically sketch. Always think about S to be just one column.
On the worker, right? Yeah, I got it.
So this is on the worker. This is what he computes on worker. He received a message from the server telling him, if I use your estimate or estimate of your Hessian, which I had, using the sketch matrix S, that's what you get. Now basically you tell him, hey, by the way, my Hessian is slightly different in this direction, and therefore you should somehow adjust your estimate of the Hessian by this message C tj, okay? Again, think about compression is not there, right? If compression is not there, I'm telling him that even though you believe my hashing is like behaving like this, actually it's happening differently. So therefore, this is the new update you should somehow use to update your belief about my hashing, okay? Not sure if this makes sense.
Yes.
Again, think about this j should approximate my hashing on this device, right? If they're the same, if my estimate of the hashing was perfect, then if I multiply this one by s, I will get some vector which will be the same as this vector here, right? Again, choose m this equals to 1. Again, if my estimate of the hashing was perfect, if I choose some random direction st, and this will be the same, I just need to send vector of zeros, which is nothing, right? This really tells him that, hey, your estimate of the hashing when sketched by this vector st was perfect. It was the same as a true hashing if you sketch it by the same vector st, okay? If there's some difference, because maybe h was not really perfect, then I just tell to the server, by the way, to update your estimate of the hashing because it should be different, right? This tells me, actually, if you really want to sketch the hashing, the estimate which you have, it should be like this one. Not like this, but like this, okay? And again, if I have now estimates of the hashings already updated, I can just compute average of them over j's, and then I will use this one as my Newton matrix, and then I can compute the Newton step. Okay. There's actually one more thing I need to send from the workers to the cluster to the cloud, which is actually this matrix here. Again, the size of this guy will be just m by m. And you can compute this one locally on a device, because you can see you already have computed this guy here. It will be basically, if m is just 1, will be d times m. Then multiply this one by s transpose again, and you will get m times m matrix, okay? So I will not send only the gradient and this guy, I will also send this quantity here to the server, but this is just m by m matrix, which is super small, okay? Think about m like 1 or 2 or 4, okay? And now basically you can ask question, okay, how should the server update the estimate of the hashing? Because he received this message, which tells him, by the way, your estimate is maybe not perfect. If you multiply the hashing by the sketch matrix S, you should get something like this, not like what you sent me, right? And actually, there's like two different ideas. First of all, if I define this y to be the message plus this, again, if I don't do any compression, then the y will be hashing times s, okay? Again, think about this one. If I don't do any compression, then the message I receive from the server, if I also add my estimate, will be nothing else, just the full hashing times s, right? Again, if there is no compression, it will be like this one. If you use compression, this will be slightly different, okay? But again, hopefully as we go, we are getting better estimate of the hashing. So therefore, this quantity will go to 0, okay? So therefore, the variance from the compression will be somehow diminishing to 0. So okay, this will be somehow fine. And afterwards, what we can do, we can just use this block SR1 update, which now tells me how to update the hashing estimate from iteration t to t plus 1. Again, what I'm doing, I'm just sketching the hashing. And now you can see everything is working very nice, because this is nothing else, just the message I received. This one is nothing else but my S transpose hashing times S. Think about this one. This is just S transpose hashing times S minus the S transpose estimate of the hashing before times S, pseudo inverse, and the same matrix as before, okay? So what is nice property of this one is that, first of all, the matrix MJ is positive, is symmetric. Also, this is symmetric. Also, this is the same as this one transpose. So also my H t plus 1 of J will be also symmetry for every J, okay? Because now see that we are still getting symmetric updates for this H. We just sketch the hashing in some direction SD, tell to the server or to the cloud, hey, your estimate is somehow like not perfect. Try to adjust using, let's say, this block SR1. We also have a different approach. in some sense, you can say, maybe I will choose some learning rate for learning the Hessians. That's in this case, beta. And we try to create some kind of average of the age. And actually, this is nothing else, just SR1 estimate, again, blog SR1 estimate when you start from 0, okay? It's the same, almost the same stuff. I prefer this one. I think Artem may prefer this update. So there are two different things what you can do. And basically, once you have this age, you can just compute the Newton direction, just using this matrix H. I think in FedNL, what you do, you have an estimate of the Hessian. You just put there some dumping, so adding some kind of like L times identity. In our case, what we do, we just make this operator omega, which really means you compute eigenvalues, and those which are smaller than omega, you just set them to omega. So you don't get, you still have like positive definite matrix here. And then also you will not get some small eigenvalues close to 0. And afterwards I do inverse times gradient, okay? That's basically what we do in this work. And afterwards you have the next iteration, which you can send to devices, okay? What is nice about this one, you still have nice local quadratic convergence, similar to FedNL, but also we have this global linear convergence for this method. Again, this one is converging globally. Of course, the rate will be much worse than gradient descent in theory, in the worst case, but in practice, it's actually much better, okay? I will show you some results. Also, I promise you to mention, like, if the choosing S is random, if this is good or not. Again, it's good because you can just compute this S on devices, on the server, perfectly with the random seeds, so you don't need to communicate anything about the S. But it's not really perfect. And so we do something about quasi-Newton methods, classical, let's say, SR1 or BFGS, they choose S to be the difference of the points. And also they choose the Y to be the difference of the gradient, okay? Why? Because if S is small in the magnitude, then Y will be nothing else, just Hessian times S. Think about what we are doing now. We are choosing S randomly, and then defining Y to be Hessian times S, right? Which is actually what LBFGS or SR1 is trying to do by defining this Y and S in such a way. But again, I don't care about learning the Hessian approximation because I already have some kind of good estimate of the Hessian on the server, right? So basically what we should really do, we can just try to learn maybe the difference between Hessian times H. Because actually I will use this information to really update my Hessian estimates, right? So maybe the best thing what you can think about could be defining S in such a way really to do Hessian inverse or Hessian minus H times S. So you're trying to find the maximum eigenvalue of this difference, okay? And use this one as your S for your formula updates and so on. And actually, in some sense, when you think about this one, it's not a bad idea. And actually, it can be also done very quickly because in some sense, what we are sending will be the difference of this one. So in some sense, you can really think about running some kind of power method to really estimate this maximum eigenvalue, eigenvector as you go, okay? So this is ongoing work now. I think if we manage to submit to conference next month, I don't say which one, but deadline 17th, maybe we can read about this one there, okay? And also basically, we also have some modification, which is this flex complex gradient differences. We can also assume I don't compute the gradient of the function, but just an unbiased estimator of the gradient. And also I can just quantize even the gradients. Basically, H will be the local estimate of the gradient. I will do some kind of like quantization of the difference. And also we can also assume I don't compute the full Hessian and sketching the full Hessian. I just need to compute stochastic gradient and then sketch it by some function. I think the proof we need that I will use different mini batch for computation of the gradient and also for sketching the Hessian. But basically we have some extensions here where you want to be even much more fancy. You don't want to compute full gradient because maybe of the nature of the problem, or basically also this takes some time. And also I don't want to sketch the full Hessian, only some kind of stochastic Hessian estimate as well, okay? We have some results there. Now think about the experiments. So in this case, we do A9A dataset in this case, the problem size is, I think, that 123 features, which is nothing. You can see what we implemented here was really this FedNL, which is actually quite slow here. It's also slow because we started the FedNL. The estimates of the Hessians have been really the true Hessians at the beginning. So therefore, basically, at the beginning, you need to suffer because we need to communicate the local Hessians to the server, okay? We somehow also compare with this blue line is this truncated Hessian approximation. Basically, which I describe I like more. And in this case, their update will be the one which my student likes much more. So again, the performance was the same. You also compare with Fed Sonia, which is some kind of like Sonia algorithm, which we proposed a couple of years back, but implemented in federative learning setting, okay? Again, for this small data set, they look all roughly the same. Now, if we go to GZ, I think GZ was like 5,000 features, okay? You can see if I have 5,000 features and I say I want to initialize FedNL using the true Hessians from the workers, of course, I just need to like wait for the full Hessians to be sent. It's expensive to send the full Hessian in the beginning, right? And also like one way to show your algorithm much better than the competitors is just to screw up their implementation, right? Maybe you can say, maybe don't start with identity for FedNL, and don't start with the true Hessian, but just start with identity, and then FedNL will be much better, maybe. And it's like fair point, we should really just implement this one properly as well. But you can see here in this case, again, using those methods, you are communicating much faster, and also you don't need to really start with some fancy estimate of the Hessians. And also for the real sim, again, this is like 21,000 features. Again, you will already have Hessian, which is like a few gigabytes in size, but still in our case, it's fine because you just compute on devices only Hessian vector products, that's it, okay? We also mentioned about the extension when you don't compute the full gradient, just kind of stochastic gradient, which is this flex compressed gradient, which is the blue line. You can see it's much faster. Also, you can see here, if I choose memory size, the M1, actually I communicate much more if I choose M equals to 2, right? If I just put iterations on the x-axis, then the dashed line will be much better. But because in this case, I put the communication, like how much bits I communicate, it's much slower to communicate much more for the sketching metrics, okay? The same here, we have 1, 2, up to 8. Again, choosing 1, it's much faster than choosing 8 because you need to communicate much more. So therefore, in practice, usually you want to choose M much smaller, maybe 1 is sufficiently good, okay?
So, sorry, Martin, there is a question in the chat.
Yes.
Actually, 2 questions from Konstantin. So let me
Three
actually
questions from Konstantin.
Yes, so it keeps coming. So please, Konstantin,
What
go
questions
ahead.
from Konstantin?
Yeah.
Thank you. So can you please describe what is W during projection in Newton step? It was several slides ago. So
You mean omega or?
yeah, omega. Yeah,
Okay,
this.
so omega is hyperparameter. So what you do here, what is this operator omega? You take the matrix H, you decompose into eigenvectors, eigenvalues. So basically you write this H as Q lambda Q transpose, okay? And this omega tells me that all those eigenvalues, which are lower than omega, let's say negative or very small in magnitude, you set them to omega.
Okay,
So if I have eigenvalues, let's say 1, maybe 100, 1, 0.0001, and minus 10, I will set this minus 10, and also I will set this 0.000 something to omega. Also
okay,
saying differently, my H here, again, doesn't need to be positive definite. Okay, doesn't need to be. So therefore,
so Martin, yeah, I got it that it is projection to positive definite cone of symmetric matrices with low bound W, and W is scalar. But can you describe what is W exactly? So what quantities do I need to compute W? Because maybe I need to have the Hessian information.
Omega is parameter. We choose, I think, omega like 10 to minus 3 or 10 to minus 2. Because again, you don't want to have this small eigenvalue and then make the inverse, right? Because this will be unstable.
Okay.
It's almost the same what is done in FedNL. You are adding this L times identity, right, for the Hessian estimates.
Yeah, but for example, that you discuss if mentioned in FedNL for L So to L, there is a specific formula to compute L in FedNL.
Yes.
This involves the difference between the current estimator of hashing in the client and the full hashing in the client. So in some sense, in FedNL, to compute this LK quantity, you need full hashing information.
Yes,
So,
yes, but again, like what we sound trying to say again, in our case, we assumed, or we somehow like claim that computing the full hashing on device is impossible. Therefore, in our case, omega is just hyperparameter.
okay.
Because it's hyperparameter, it also negatively affects the convergence rate, because again, if you just say some quantity, you know, it has to be like worst case analysis and therefore basically be terrible, which is terrible in theory, right?
Okay.
And therefore we are trying to work on some small extensions. Hopefully we will finish on time, where basically we really address this issue of having some hyperparameter omega to basically obtain much better algorithm. Because still I know this weakness. On the other hand, it's very good in practice, but still currently we just treat this omega as hyperparameter. That's it. Okay.
Oh, yeah, thank you. Second question, can you describe what is a memory footprint in clients? Because I have lost slightly. So what clients during the optimization procedure should store?
Okay, so the client just store his own data, will know what is WT, compute the gradient, and then also compute the gradient times this vector S. Again, think about memory size to be 1. So basically the requirements for the client is to be able to store 3 vectors of size D. That's it. This 1 vector of size D, my model, my gradient, and also Hessian vector product. So basically 4 vectors of size D. So basically the footprint of the client is just storing 4 vectors of size D. One is the W, the model parameters, which by default you need to store. The second one is the message you receive from the server, what is believed about the sketch of the Hessian stored on the server. The second thing to compute, or the third thing you need to store, is the gradient, which you need to store even in every algorithm, right? So the only additional thing what you need to store is just 2 vectors of size D. This one and this one.
So HGT is not stored on the client. It's obtained from the master.
You receive this one from the cloud.
Okay.
Again, this one tells you if I sketch the local estimate of the hashing which I have on my cloud, this is the vector you're getting, right? And you're just telling him, actually, the 2 you need to adjust, right? Because this is what you believed, but this is what is really true about my local hashing now, okay? If you sketch my hashing now with this vector S, this is what you will get, and this is basically what was your belief, right? So basically, send him the difference between the truth and his belief, and send, hey, you need to update your belief, right? And basically, some discuss here, if you think about this one, now if you don't use any compression here, if I multiply the new estimate by the same S, you will exactly get this Y. Can you just make this simple test? If I multiply this one by S, I will get exactly the Y, which is just the Hessian times S. So basically, after he updates his belief, if there's no compression, then the vector I would send to him would be identical to this guy. So this difference will be just 0. So basically, after doing this one update, then he's adjusting his Hessian estimates such that if I would multiply this Hessian estimate by the same vector S, I will get perfect answer if there's no compression, okay? If this one is gone, you can see if I multiply this one by ST, you will really get YT. Because this is actually the block S7 update. That's how it is defined, okay?
I see. Yeah, thank you. Oh, by the way, this optimization problem, which you find the best possible sketch S, it's mostly like just thinking about it, yeah, but it's not practically computable because
actually, yes, we have been thinking about this one, but I still believe that our procedure can maybe compute this one almost for free. Again, if you think about power method, if you want to compute this one by power method, right? You choose some S, then you will get some y, right? What if I choose the next s to be this y, right? As you're progressing, you're getting better estimates versus some move, right?
Yeah. But
Again,
to do this, you need to
like,
information about.
if you wait like 1 month and 5 days, it should be submitted to the conference. I don't say the name. But basically, we will also put it on archive afterwards or before, okay? But again, I believe you can really just use this one. We really just try to find what is the best S. If you really want to minimize this quantity, basically the spectral norm between the Hessian estimate and the true Hessian, you really want to choose S, which will be the maximum eigenvalue, eigenvector of this difference, right? Because currently we just choose S randomly, which is not the perfect. The perfect should really maybe try to maximize the difference between this and this, right? My belief and the true Hessian.
Yeah. Nice if possible. Just even intuitively, you.
Yeah, that's the intuition which we have, and now we are working on this one. We have some results, they are quite interesting, but still the theory is a little bit struggling, only because in FedNL it was nice because you assumed you can compute the Hessians on devices, right? So basically in FedNL, this LT was really just measuring how much my local estimate of the Hessian is far away from the true Hessian which I computed now, right? So therefore, basically, this is nice because we can compute this one in runtime. We can't because we don't even assume that we store the Hessian, right? So we can't.
Yeah, thank you.
Therefore, we have this omega as a hyperparameter to choose, which is the weakness currently of these two papers which I mentioned.
Yeah, thank you very much.
You're welcome.
Last question. Can you just maybe for fun, can you say if you know the time during training for logistic regression for A9A data set?
But like, what do you mean like time? Like how long?
Like real time? Yeah, I guess. So it's I understand maybe it was prototype.
So it was like very funny because it was really just 0.00, maybe 0.1 second. I tell you how. I said, Artyom, could you run it? That's it. Just ask the student to do it and it was done. So I have no clue. But still, like, I think that A9A data set is like super tiny. So this could be like a few minutes maximum.
Okay.
Because again, you don't compute Hessians, you're just sketching Hessians. So I would really believe, if I'm not mistaken, this was just maximum few minutes to run.
Okay.
Also depends how many workers you have. I don't know how many workers he had. Maybe he had like 4 workers, 8 workers. I don't know. But again, like the computation is very fast because computation again, A9 data is super sparse, right? Computing gradient is nothing. Again, sketching Hessian is also nothing because we don't compute the full Hessian. We just sketch the Hessian. Okay. So I believe this was like nothing, almost no time. And then the most expensive part was doing the truncation with the omega, but still in this case you have just a matrix which is like 123 by 123. So eigenvalues of this one is nothing to compute. It's super fast. Okay. So therefore I believe this was pretty fast. There was no issues really running this one. I know what was much harder was this data set here, because in this case you have 21,000 times 21,000. So I believe in this case computing the inverse or even truncating was much more expensive. But still, someone said it needs to be done on cloud so they can do it, right?
Thank you very much.
You're welcome. If there's any more questions, please ask.
You can, for now, you can continue. There are no any more questions in the chat.
Okay, so I think I'm done. So now you can ask questions, right?
Yeah. Thank you. So yeah, if you have any questions, then please to raise your hand or just post the question to the chat. Yeah, I think we're running a bit out of time, but yeah, maybe we have still time for a couple of questions if you can stay around. I would have one more like kind of maybe 2 questions to start this with. You at the beginning you mentioned that okay, you do not focus on partial participation, but with your method you have like your global memory scales okay with n, And if you kind of scale it to some like a large application, that might be quite a problem. And even like if you have a very powerful server, it might not be it might not be feasible, right? Do you have any kind of idea how to cope up with that?
I have idea.
Okay.
Which is much more going to the disco.
Okay.
So it's different project we are working currently,
Mm-hmm.
which is trying to use the ideas from disco paper
Okay.
to really see what I can do in such a scenario where I
Mm-hmm.
don't have full participation every single
Mm-hmm.
time. So I would not say, yes, there are some ideas. It's not
Mm-hmm.
currently in this talk, because
Yeah.
this was just trying to speak about this flex and how we address this issue of the storage from devices to server. But there's ongoing work. Again, if I will be lucky enough, again, 17th of next month, you can read about this, if I will be lucky enough.
And one other question regarding the kind of implementation of like kind of system perspective of what you do, because like a standard case is that for like downlink, so from the server to the client, you only do like download, and each client download the same copy of the model, right? While what you require is essentially to download the actually sketch with respect to your own estimate of the hashing, right?
Yes, correct.
So in that sense, like, do you have any idea like how much that would be kind of different in terms of runtime if you would run it on kind of some standard system implementation? Like how much would that actually like slow down the downloading?
Again, like in some sense, like when you like, what is the beauty of using Newton method? The beauty should be once your estimates of the hashes are good enough, then you just do only a few iterations, right? That's the hope. And also saying that, you know, you need to store so many matrices on cloud, it's true, but you don't need to store them in the memory. You can just put them to hard drives, right? So having, let's say, 100 terabyte hard drive is not too expensive on cloud. And also we require that I need to compute this Hessian times S, but actually I don't think you should really do it everything at the same time, right? Again, if you just do only a few iterations of this Newton method, maybe receiving the updates in the whole day is maybe fine, right? So I don't need to send this one very fast, very, you know, in runtime very quickly in parallel. I don't need to. Can really just send this one to workers, they can receive the message, and afterwards they can compute the gradient and the Hessian vector products and send it to the cloud. That's fine. Then they can wait for, let's say, a couple of hours. That's fine. I don't care about, again, because again, the whole idea is that I will not communicate overall so much, right? Because again, like if you think about classical gradient methods, square root of kappa or kappa times log 1 epsilon for storing convex. In this case, they're speaking about 10 iterations. Should we, I try to like think about, I try to design some algorithm and I just need only 10 steps, 10 communications in practice. And the issue is how can I build some hard data set which will need much more steps, not 10. I know my postdoc told me, hey, Martin, just don't start with 0 for logistics because 0 is a good starting point. Start with something terrible, then you will diverge. I say, but I know 0 is a good starting point, therefore I start with 0, right? So the same basically what they did in Disco paper. Basically, they said, don't start with 0. So what they suggested in Disco was every single worker, it was Convex problem and so on, every single worker will just start, compute his local minimum estimate. I compute average of those, and this is my starting point. Again, why would someone start with some nonsense where you can easily estimate some good starting point, right? Think of this one. I minimize each function separately on devices. You'll get W1 up to WK. And I compute average of those stuff together, and that's your starting point. I think there's some small change. You do some kind of regularization. Doesn't matter, right? Again, why should someone start with something which is stable, right? And then say, hey, I have a hard problem because I started wrongly, no. But still, usually in my experiments, usually 5-10 steps, I'm done if I start with some reasonable starting point.
Okay, thank you.
But
Any other yeah.
seeing
gotcha.
this one, if you have some good hard convex problems,
Mhm.
please share with me. Okay.
All right. So yeah. Thank you, Martin, again. That was a very nice talk.